Well, thank you very much. This is my second visit to YouTube in the last 6 months. And some of you were in a talk that I gave in the engineering building. Could you please raise your hands, those who were there? Could you please raise your hands, those who were not there? The same number. Okay, so basically there I spoke about what I called connecting dots in a flat world. And the essence of the talk was that I was trying to motivate some of the other students to come to computer science because I think it's the future of everything. So I wasn't sure how much of that I could say, what I said there. So I would just mention one thing. But before I go there, I decided to sort of design a talk towards this golden nugget thing. So that's my vita. I was a professor of computer science at the University of South Carolina for many years. Then I went to work with Microsoft, University Relations and Research. Now, since October 2007, I am with Google searching. My PhD is from London University in biomedical engineering. My master's is from Cine Star EPN in Mexico City. And my BSEE from YouTube, from 1970 to 1973. And this is the abstract. Those who came to that talk sort of see the same thing. That same thing, that we have created an incredibly interesting infrastructure over the last 25 years. We have data sensors collecting data 24 hours a day, 7 days a week. We have incredibly large amounts of data all over the place. And literally, we don't know how to process that data because there is so much data we never had in the history of humankind. So much data available to us. So in that presentation, I sort of presented what's going on. And the talk was, hey guys, join us in the quest of doing this data analysis. And because it was more generic, I did not mention the specific algorithms. So today, to celebrate the 2008 Golden Nugget Awards, I decided to do the following. First of all, I will discuss with you my favorite data mining algorithms. They told me I could do a talk on whatever I choose. So, but if I do that, and then I will try to, because this is a mining school. There was a mining school, right? The college, Western College of Mines. I thought, well, it would be interesting if I connect data mining, which is exclusively computer science, to the real mining, to the gold mining. So, is there any miner here? Anybody from metallurgical or whatever mining name around? No? So I can say anything that is improperly mining, illegal mining, and nobody will do it. So, okay. So stay tuned, miners, because I hope it's going to be fun. So I mentioned that the world is flat, that it's Spanish scale, and that in 1490, and that was a disruptive change in the culture. Spain, which was not even a country then, became the most powerful nation of the world. And then through mining of gold and mining of silver, etc., they became the main power of Europe and then the world. And then we in the Americas suffered the colony, and eventually the economy changed, and all of a sudden we are living in an economy, if we survive, of course, the most recent crisis. We are living in an economy where the world is no longer flat, which means that, round, which means that we are actually in a world that is strictly flat because we are talking all the time to people in Zurich, in Bangalore, in all this world. And in fact, the young man who was talking about the algorithm, where are you from? Wherever you are. Yes, where are you from?
India.
What part of India?
Calcutta.
Calcutta. So he is a perfect example of this flatness of the world. How many miles do you have to travel to go from Calcutta to Otasa? Give and take, 1,000.
14,000 miles.
How many?
14,000.
40,000?
14. One board. Yeah.
A lot of miles. So, so he is an incarnation of the times that we live. There are many faces that I see, people who come from China, like my best of friends. What is your name? Yes, you. Yes.
Green Drain.
Where do you come from?
I come from China.
Yeah. You figured that one. What does you come from?
Hunan province.
Okay, so I asked if you came from China because I figured you were from China. So these fellows that you have here are an incarnation of precisely that concept. We no longer live in a world that you have to travel all of your life, literally, do a journey that will separate you from your families. Have you been to Calcutta or your province lately?
I'm planning to go this December.
But he's planning, right? So he doesn't see that as a foreign conclusion. It's possible to do it because they have airplanes. Probably you talk to your parents using Monash.
Yes.
Say yes so that they listen. Yes, so we live in a completely different environment, in a completely different world. So the thing is that change in the world came across because of technology, because of computer science. And the world that inspired that idea are actually the book that sort of summarizes all those ideas is the book by Friedman, The World Flood. And he has a new book where he now talks about the need for doing stuff. Okay, so this is the mining part. Because we live in this completely collaborative world where I personally interact with people in Zurich, in London, in Beijing, in Bangalore, not in Calcutta, but in Bangalore, in Buenos Aires, New York, San Francisco, whatever. Constantly. I figured that it would be nice to give you another example of a mining company that used the power of the internet to go a step beyond. This company, have you heard of this company, Gold Corp? Guess what they do? They mine gold. Right? So this company was in the middle of a crisis in 1999. And they hired a guy from Wall Street. He escaped with this crisis. And he went to the company which is based somewhere in Ontario in Canada. And he said, well, you know, the company is doing okay, but they could do better. He went to an open source conference in Boston where he saw that the best minds of the world were working on sharing the OS Linux. And he said, well, maybe if we share the geological data that we have, maybe somebody might help us to find gold. So he came back to Ontario, to his mine, and he gave the miners the idea. And they said, are you crazy? How can we share this data? That's, you know, what makes us rich. Well, you know, think about it. If we put all of the geological data on the web, the effect of that is that the best minds of the world will help us find where gold is. And of course, because we own the mine, even if they know what it is, you know, they cannot, you know, remotely have an arm that, you know, can get the gold out of it. And the incentive that we will give them is we will recognize them, we will give them a prize. And moreover, they will be recognized worldwide, and they will get a prize. So these guys did that. So they opened their geological data, they put it on the web, and the rest is history. That's what they gave away. And there were many entries from all over the world. And guess what? The first place came to a guy who lives in Australia. Second place, to another guy in Australia. Third in Australia. These guys know what they're doing. Then actually, so the first, second, third, fourth, fifth, sixth place to geologists in Australia. A few in Canada, but actually a bunch in Canada. But the best entries were from Australia. Obviously, these guys never went in the mine. I mean, that when I read about it, that blew me away. Because these folks in Australia got the data from somewhere in Canada, and they found they did statistical analysis, right? So they found locations in Ontario where there was most likely to be gold to be found. So they sent back the the estimates to the company in Ontario, and 80% of the time, those estimates were accurate. And as a consequence of that, Gold Corp became from there. By the way, this is Google Finance Wall Street. From there, I mean like 0.9 to 47.50. That was a tremendous success. Now, the final thing, when you think about it. So what is involved here? Of course, there is gold, there is mining, there is statistics, there is mathematics. So you are in a university founded by diggers, by miners. Okay? And this country, Mexico, which is South Rio, was a known country for gold. So rich was the country, and Peru also, that from 1550 to 1820, Mexico and Peru were the principal sources of gold and silver for the empire that was built for Charles V, when he said that under my kingdom, the sun never sets. Most of the cities founded in Mexico during those days, including my beloved Chihuahua, San Luis Potosí, Durango, Zacatecas, Guanajuato, Pachuca, and Tasco, all of those cities came about because of mining. So when you go to any of those cities, the first thing that you will notice there are no rivers. Like when you go to San Luis, or you go to Atlanta, or you go to whatever city in the United States, there is a river because those cities were founded by farmers. Those are cities founded by miners. So mining is in those days was not a science. For example, according to Francisco Almada, a historian of Chihuahua, the Santa Eulalia mines, which is the cause of the founding of the city of Chihuahua, was discovered in 1703 because a mule fell. And then as he was going down, the mule hit silver. So the guys who went to rescue the mule, that's how the city was founded. It's incredible. So it was the mule was in a ring. Maybe the name of the mule was Eulalia. Who knows? Right? And that's what happened. So mining in those days was an art, actually an accident. So, but now we have the scientific tools to make it possible. So, what is the science of data mining? The science of data mining is gathering all kinds of data. In any shape or form. It could be data from geology, it could be data from statistics from health, whatever kind of data, and putting this data to play in a kind of a sandbox. You have seen children from India, from China, from Peru, from Mexico. When you put those children together in a sandbox, they find a common language and start playing. Okay? You have noticed that probably, right? So data, if you put it in a sandbox, and you're smart about it, we can find sandboxes where we can have data playing together. What is that sandbox? That sandbox is entropy, information. Not information a la IT, what you go on in the return server. I'm talking about information a la Shannon, a la data, a la statistics. So if you extract information from your data sets, then all of a sudden you put all of the data sets playing and talking in the same sandbox. And then regardless of the origin of the data, you can actually make this data work. And then hopefully with that you create higher order representations that then you can put in maybe graph form or something like that, from where you can do inferences, which will lead to decisions, and hopefully to knowledge and better ways of living. So that's, in a nutshell, data mining. Now, data mining has a kind of an interesting pedigree in terms of its origins and science. It comes from artificial intelligence, machine learning, statistics, basic networks, and databases. By the way, I speak in this funny accent, right? You have noticed that, right? So I speak with this funny accent, and sometimes I say things that don't make sense. So, because we have a small audience, If I speak and say something that doesn't make sense and you have to ask, just ask, okay, no problem. I will not be, in fact, I will encourage you to ask questions. Normally, I bring kisses, Hershey kisses. And I throw them away when people ask questions, but because of the timing that I have, I couldn't do that today, and I didn't do it last time. So actually, I brought Georgios last time. I forgot to bring Georgios. So, relax, it's going to be fun. So, what are the known data mining algorithms? I went through my history of algorithms, and I put the ones I remember. This is a trees, clustering, nannies, etc. Is there any algorithm missing? My dear fellows in computer science? Can you find one that's missing? I don't know, I'm truly, this is not a captious question, I'm truly asking. Yes?
Support vector machines?
Yeah, okay. This is kind of an architecture. Support vector machines. Thank you very much. Hola. The triggers are coming. Yes.
Thank you.
Fuzzy logic.
Yeah, fuzzy logic, thank you. Fuzzy logic. Yeah. Fuzzy logic is kind of an interesting story. The guy from Berkeley, Lofty Sad, invented it. But he's not there. There are reasons that I can tell you. Are you firm with this thing? Yes, you are. So probably I should tell you why he's not there. Okay, so the ones that I kind of like more are the ones at the very bottom. Bayesian networks and Markov chains. So I will sort of concentrate more my talk on those two. Because as they already told me, speak about any topic you like. Well, I like those two. So I will talk about those two topics. There you go. So what is a Bayesian network? A BN is a directed acyclic graph in which the nodes represent variables in a domain and the links represent connections, causal connections. So if you have a domain of say A, B, C, D, E, F, and G, and then you can somehow say that D is influenced by A and F is influenced by D, then you can put something like this. And then if you have the way to qualify these connections via a conditional probability, where this conditional probability is the P of D given A, then you have a Bayesian network. For example, it might be that some of the variables might have 3, 4, 5 data values, etc. This one on the left would be a singly connected network, and this one on the right, as you guys know, is a multiply connected network. And there are distinctive issues that we talk about that. So, I'll give you an example. This example is taken from a classical paper by Larison and Spiegelhalter, where they took statements from a book of medicine. Since you guys are going to become bio something, what is bioscience? Yeah, that. So, probably this will help. So here you have a statement that says tuberculosis and lung cancer can cause dyspnea with equal likelihood, etc., etc., etc. Read the statement. Notice that I have in red some terms. Okay? Notice that. Okay. So if I am a computer science professor and I go to work with the guys in Texas Tech and I read something like this, then I could design a Bayesian network that goes like this. The situation causes tuberculosis. Smoking is a cause of cancer and bronchitis. Dyspnea is caused by bronchitis, tuberculosis, or cancer. And X-ray is positive means we have tuberculosis or cancer. So that's your network. Yeah, that's your network. Now the next thing you need to do is you need to put numbers there so they can actually play. So as Shakespeare said in Midnight Sun, I would like you to commit this image to your memory. Please look at it hard and try to remember it. Look at it hard and try to remember it. Why? I see your face. Look at it hard. Why? Because I do it then. And I will ask on this demo the owner of an assistant a very dear friend of mine. You know who I'm talking about? Wake up, Rodrigo. So this is a tool that I built when I was at the University of North Carolina. And in this tool, I call it Basic Nervous Systems, and Rodrigo is going to be my patient. So Rodrigo is coming to the clinic, and then so I told you to commit that draft to your memory, right? So we have A is a situation, F is smoking, L is no cancer, etc. Notice that all of these variables, to make it easy, are binary. So you smoke, you don't smoke, you went to Asia, you don't go to Asia, you have lung cancer or you don't, etc. Okay? So that's the network. Then I will open another view of the same system, like so. And then Rodrigo comes one morning from the hospital. And yeah, there you are.
Do you want me to go there or not?
Well, as long as you can do what I'm asking you to do,
Okay.
that will be fine.
I'll do it from here.
So Rodrigo is right there. And he comes to the hospital, and you know, he has a great voice. You know that he was a opera singer? I mean, I'm not kidding, right? I learned this stuff, you know. So he was an opera singer. So congratulations to him. But sadly, his voice is going sour. So the first thing that I noticed is that he has dyspnea. What is dyspnea, my friends? What is dyspnea? Problems breathing, right? So look at this thing on the left. So these are the nodes on the basal network, right? And so we can say whether he has bronchitis or not, dyspnea or not. So when a patient comes from a clinic, I bring this data set, or actually this model of the patient, and I say, well, typically when somebody comes to the clinic, it's because they have a reason. And maybe they think they have cancer, or maybe they think they have tuberculosis, and you can make this into So when Rodrigo speaks, say anything, Rodrigo. It's not working.
Buenas tardes.
No, but it's not working. So I know that he has deep dyspnea. He cannot breathe. He has problems breathing. So what do I do here? By the way, I think that the chance of he having cancer are very minor, 5%. So I said, well, no, he has dyspnea. So that's my first observation. So I click here and I say, yes, he has dyspnea. And notice what happened to the lines. All of a sudden, cancer went from 5 to 11. Interesting. So I asked Rodrigo, are you a smoker? No. He said, of course not. Okay, no. So I said, no. Fine. So I entered that evidence. It went back to no, right? Now it's again 0.2. And then, so what would you do, Rodrigo? You were a nurse. What would you do? You would probably check for bronchitis, right?
Right.
So he gets the stethoscope. I drip, and he breathes deeply. And I check. There is a little bronchitis, but not too much. So I said, well, maybe. And then, you know, Rodrigo, I think you have a bad flu or something. Get this aspirin, get out of the room, and next patient. And Rodrigo goes away. I save that information. Then 2 weeks later, Rodrigo comes back. The dyspnea has worsened. And then he tells me, you know, doctor, but he knows me from my childhood, so he would tell me, no, I lied to you. What? I am a smoker. Oh my God. So then I bring data. And I said, oh, so you were a smoker. So I changed this from no to yes. Oh, okay. So now we went from 5 to 11 to 2 to 45% having lung cancer. Okay, now, so I have some options here. I can say, okay, so I probably want to take an X-ray. But he might be pregnant, so I don't want to do that right now. So maybe what I should do is I probably take a sample of his blood and see if he has tuberculosis. I know he doesn't like to be taking blood, but I try. So I do, and not really. And now the cancer went from 45 to 47. So, well, you know, we have to miss that pregnancy. I know you really love your being there, but we have to take an X-ray. So if you take the X-ray, and this happens to be positive, then my model tells me that Rodrigo has a very high likelihood of pregnancy. So what is this telling you? It's kind of a fun game, right? And that's what they do with us, the doctors. So if we go back to this thing, here. So basically, the beauty of this Bayesian network thing is that you can have hypotheses and you can play all kinds of what-if scenarios. And whenever you do that, all of the nodes immediately update the P of X given Y information in the entire system. You so have fast it is, right? Now, I have other networks that are significantly bigger with hundreds of variables, and the speed of execution is extremely fast. How come that's possible? Well, the beauty is in the mathematics. The second thing that is interesting is that whereas in the traditional rule-based systems and other systems that deal with uncertainty, you have what is known as non-monotonic reasoning. Here, you can do an assertion, test it, and if it doesn't make sense, you can retract it. The example was when Rodrigo told me that he was a smoker, and then we retract that, and then we change to smoking, and then that completely changed the outcome of the node that we were interested in, which is the node with a non-cancer. So these guys have tremendous, nice mathematical properties that I like to share with you, some of those properties. So these networks, there they are. In fact, what they have is, in every link, there is a set of conditional probabilities. And the conditional probability becomes like a table. So if A, for example, is a variable of 3 values, and B is a variable of 3 values, you might, after doing an experiment, come with a conditional probability that tells you that these are the most likely values. So when A1 is, when A is equal to A1, the most likely value for B is B1, etc. That's the first thing. Second thing is that all of the links have such tables. Now, how this operates, you saw the example, let me tell you what is going on. So I enter evidence, and when I enter evidence, I simply assert a node to be of a certain value. In the case of the smoking, non-smoking, I say yes, I say no. So when that happens, I assert a value on the node, and then that has the consequence of launching a bunch of calculations. So the node re-estimates its probability. There are 3 vectors here, the probability vector, a vector called the pi vector, and a vector called the lambda vector. Then these 3 vectors are recalculated, and then messages are sent out to the entire network, telling the other nodes, hey, there is new evidence, you better update your values. So messages are sent in the way of what is known as lambda messages to their parents, and pi messages to the children. So this would represent messages going up and down. And as every one of these messages propagates into the nodes recalculate their vectors, and then if there is more evidence to be propagated, they will do it. And that happens very, very fast. So the belief or the probability is computed as follows. In every node X, the probability is calculated by the product of the lambda vector, which is the evidence coming from all of the parents, and the pi vector, which is the evidence coming from all of the children, and then normalized by an alpha. And then how is that done? So the pi vector is calculated using this formula. This formula, what is this, my friend, by the way? What is this thing that is here? It's the conditional probability of node A influencing on node D. And then, so the vector is the multiplying of that conditional probability, that length, by a message that D is sending to A, from D to A. Right? So that's that calculation. Likewise, lambda is calculated by sending those messages to B. So now the messages themselves need to be calculated. And again, the beauty is that there is the same set of equations. So when you have recalculated your vectors, your belief, your pi, and your lambda, then what you do is you send a message to your acquaintances. In this case, say D sends a message to this parent, and it does it through the conditional probability, and the message is this equation. So again, you see lambda is calculated by the conditional probability being used to get the node lambda through this probability, to this conditional. So the lambda vector and this table become the message that is sent to the node. And this happens for each and every one of the links that exist in the system. And the pi is exactly the same thing. So basically, you have a lambda, which is the vector that you have here. You send that lambda through another set of lambdas, and you send that message to you. So in this example, it's an animation. Please don't go. See, that's what happens when you start getting bored. So you get the evidence, and then you calculate the neutrality vector. Then you propagate a message to your parents, to your children, and because those nodes A and H, E, F, and G got new messages from the parents of the children, then you have to estimate their new probabilities. And when they do that, then you have to also send new messages to the nodes around you. So that's how it goes. Now, how do you build these things? Well, you build them by interviewing experts. You go to Texas Tech and ask the experts how they will do the networks. I've done that. You can also get a bunch of data, and then you do machine learning, and you learn via anthropic methods the structure of the data. And then you can use it and massage it with the network, with the experts, and you can get improved network that you can then test via this, help me, the method that gives you the yield. What is it called? I will go. So that makes to see how good the model actually behaves with the data. And then you can also combine automatic and methods. Now, I mentioned to you that there are certain types of networks that have a little problem. And the little problem is if you start sending data, or rather messages, up and down, say, this loop, then there's going to be a situation where you have an infinite set of messages going around, right? So it's a cycle, right? And you guys, computer science, immediately see that. So what do we do in that case? Well, what we do is, in essence, if you think for a moment, the whole system is nothing but a chain, a product chain, that computes the joint probability distribution of that set of. And in every case, you have the P of node given the P of its values, right? And that's the classical conditional chain. So if you can do that, then using other methods, then we're okay. So it so happens that you can use what is known as clustering algorithms to go from a representation where you have a graph of nodes to a representation where you have a joint tree or a tree of clicks. And this is precisely what you do like so. So that particular network, you remove the arrows of the legs, then you join and triangulate the graph. That's the triangulated graph, triangulated under the graph. And then you simply do an algorithm, like the minimum degree algorithm, where you build a junction tree. And the result of that is a set of clicks, such as, say, this one, EEC, where BEC is actually the probability that exists by the collection of these three nodes. Okay, and as long as that is equivalent to the joint parity distribution, then you can have a set of potentials. This is how they're known. Potentials of the clays that when you do the product, multiplied by some normalization constant, gives you the same joint parity distribution. So it's just a important representation with the difference that this is much faster than using the algorithm that I just presented. So the same idea. Now, between, say, click AB and BEC, there is another node, which is kind of the linkage between the two. And the whole structure between AB, the node B, and the BEC click, that is known as a potential in the technology. So the important point is that you create a representation that is actually totally equivalent, and you can come to the same conclusion as well. So I have done a lot of work in this area with my colleagues at the university, with our colleagues in many institutions, and we created systems that did resource allocation, negotiation, blah, blah, blah. And this thing we did for years at the university, and then we came to do all kinds of interesting problems, and then we came to the point where we had so much data that we negotiated with Walmart. Yeah, these guys in Fayetteville City, to get a data. So I got a data at the university. In those days, was probably the largest machine in the university. I forgot how many terabytes we had. And we put a Bayesian network on top of the data system. And we did a lot of interesting things that I cannot tell you. Because I would have to, ask the guys on top of this to help me with you. So anyway, that will give you the gist of what we're doing. So anyway, I want to sort of change a little the topic, because I said that I wanted to tell you my two favorite algorithms. And how much time do we have? 10 minutes. Oh, okay. So I said that there are two algorithms that I like, right? One is Bayesian networks. I know I am enamored with Bayesian networks because they provide you wonderful computation. But the other one that I said is pretty cool is Markovian chains, right? So Markov chains. So this brings me to the topic of PageRank. PageRank is an algorithm developed by now what is Google, replaced by Google. And the problem is as follows. Traditional libraries keep the information in post. And so they have somebody who does the index, etc., and the index is relatively static. Well, in the web, as you know, this is huge, this is dynamic, is constantly changing. So creating an index for that is a remarkably difficult task. So search engines do the following. Typically, they create these wonders, what they do when they do searching, in two steps. And I'm oversimplifying, but you can think of this in two steps. One is they try to extract information from the query and then associate that information to certain pages using methods known as information retrieval. That's the first step. The other step is, okay, so now we know that. Now, what are the best pages that we can provide to this person who is asking for, say, the term engineering? So there are two sort of separate but very related problems. One is we need to find out what pages have the terms that users need. And second, we need to provide to those users only the best pages possible. So we need to do a ranking. And that's the second part, the ranking algorithm. So, because it turns out that the ranking algorithm is a nice Markovian problem, I'd like to tell you a little bit more about it. And this is very much a math machine. So, search engines. So this is a typical search engine. And we can follow the steps of what's going on. First of all, there are a bunch of crawler modules, tarantulas, that go on the web and get information. They get the pages here, and then they collect them in a crawler module, and then they put them in some sort of a once they get there, the next thing is that there is an indexing module where where a bunch of indexes are created, including, for example, something that is known as the economics index. And then that happens every now and then, every 24 hours, every 6 hours. And because there are just a few billions of pages, this takes a lot of time. Then Rodrigo wants to find if I'm right about my diagnosis of cancer. So he enters some query, and the query goes to the query module, where it goes to the indexing module, where the best pages are then looked at from the context index. And then the ranking module selects the best pages according to that content, and then so on and so forth. So what is the content index and how it works? Well, for each term in the index, what they have done is they have put a bunch of pages and using what is known as an inverted file structure. And basically what they do, for every term, say Florida, minor, Texas, etc., they put the page numbers where the term exists. So we know that term 1, Florida, is found on pages 3, 117, 3, 9, 116, etc. Then you can be a little smart. So then you can, what if we add a little semantics to this? So then, for example, if you add per page some semantics, like is the term in the page title, yes or no?